everyone. So here's our first example for angular momentum. So we have figure 11-13 shows an overhead view of two particles moving at constant momentum along horizontal paths. Particle 1 with momentum magnitude P1 equals 5 kilograms times meters per second has a position vector R1 that will pass 2 meters from a point O. They're giving you the R perpendicular vector with that 2 meters, which is right here. Okay. And then it says particle 2 with momentum magnitude P2 equals 2 kilograms times meters per second has position vector R2 and will pass 4 meters from point O. And again, they're giving you the perpendicular vector right there. That's what they're giving you. What are the magnitude and direction of the net angular momentum L about point O of the two particle system? So in order to find the net momentum, L, we need to find or add up the momentum from particle 1 plus the momentum from particle 2, the angular momentum, I mean. First and foremost, I'm going to see which one's going to be positive, which one's going to be negative. When we have linear momentum that could go counterclockwise, that's the positive, and linear momentum that could go clockwise, that's our negative. So you can see that P1 is going to go by this, and if it did rotate around particle O, or point O, whatever they're calling it, that's going to be a counterclockwise rotation, which means that our angular momentum for particle 1 is going to be positive. And then if P2 were to rotate around point O, that would be clockwise, so that means our angular momentum 2 is going to be negative. So this is actually going to be a negative sign. Now this equation for angular momentum, we know that's going to be equal to R cross P, our position vector crossed with the cross product, right, with our linear momentum vector. Now here they do give us linear momentum, so we don't have to use momentum equals mass times velocity here. We can just use our linear momentum. And in this case, usually if they give us like this angle right here, we would use L equals RP sine theta, again, because this is a cross product. But they actually don't give us that angle here. They're giving us instead this perpendicular vector here. So instead of using the sine, we can use the perpendicular vector, and that's going to have the same linear momentum as it goes across this part right here. So we can just then multiply those things together because it will be the sine of 90, and that makes our life much simpler. So we end up getting L, our angular momentum, is equal to that perpendicular R vector times just our linear momentum for both. Okay, so now plugging everything in, we get the total angular momentum is going to be the angular momentum of particle 1. So that will be R perpendicular 1 times P1, and then minus the angular momentum of particle 2, which will be our R perpendicular vector of 2 times P2. So plugging in our numbers here, we get the perpendicular R vector, which was 2 meters for particle 1. So 2 meters times the linear momentum of particle 1, which was 5 kilograms times meters per second, minus the perpendicular R vector of particle 2, which was 4 meters, times the linear momentum of particle 2, which is 2 kilograms times meters per second. So here we get our total angular momentum is equal to 2 times 5, which is 10, minus 4 times 2, which is 8. So we end up getting 2 kilograms times meters squared per second. That's our unit for angular momentum. And then if we look at the direction for that angular momentum, we're going to use the right-hand rule. Now, the net linear momentum about that point is going to be clockwise because this is a positive number. And what we can do is we can kind of point our fingers in the direction of the R vector, curl our fingers in the direction of the clockwise vector. If we're looking at the page, clockwise momentum vector, and then we can see that our thumb is out of the page, which makes sense because it is a positive angular momentum. So we would say this direction is out of the page. If you're over to draw an out of the page vector, we draw it as a circle with a dot in the center. Into the page is a circle with a cross in the center. You kind of think of it as an arrow either coming out at you. So the dot of the arrow is what you see when it's coming out of the page. Into the page is you're looking at like the feathers of the arrow crossed into the page because going away from you. So that's how you would draw it if you were to draw it.